Hello everyone. In this video, we are going to talk about the last signal model and the pi model of BJT. BJT, bipolar transistor, bipolar junction transistor. To begin with, I think we need to talk about what is bipolar junction transistor. And because of the problem of the syllabus, I cannot cover all the details. But I just want to tell you, if you are doing the electronics course, you should know at least some of the basic elements. One of the basic elements that you need to know is the diode. And what is diode? The diode is basically a unidirectional device. If you have a resistor, the current can go in one direction. Equally, it can also go backward. Either way, it will work. So if you are going to plot the characteristic of a current against the resistor, then in the positives, when the current is going in one direction, then you have linear relations between current and resistor. But equally, if the current goes backward, you will also get the same characteristic. So basically, the resistor itself is a bidirectional device. It's a bidirectional device in the sense that the current can flow in either direction, or upward or downward in this case. But how about diode? Diode is a unidirectional device. When you have a voltage across the diode, initially there is no current, but after you get a certain amount of voltage across the diode, then suddenly the current goes up. So this is the situation of a diode. But how about what the reverse direction? What if we reverse the direction of the current, say in this way? There won't be any voltage. If you do that, right, say for example, you reverse the voltage, would you have any current? The answer is no. So in this case, it should be voltage. Yeah. If the voltage is negative, then the current will be very small. So small to the extent that you cannot even measure it with a multimeter. So in other words, you may have some current, and this current is so-called the saturation current. But you won't be able to measure it with a normal multimeter. So this is the situation. The current can only go in one direction, but not the opposite one. So this is the thing that you should know. We should be aware of. So now I would like to talk about the characteristic of the current against voltage. I'm not going to go into any theoretical analysis. I'm not going to derive it. I just tell you just straight away. For a diode, you will have this kind of relationship. V over Vt minus 1. And what is IS? IS itself is a so-called saturation, reverse saturation current. Reverse saturation current. And what is VT? VT is so-called thermal voltage. At room temperature, at different temperature, the voltage will be different. At room temperature, VT is equal to 25 degrees Celsius. So this is all about a diode, and I'm not going to talk too much about the theory of diodes. If you want to know more about the theoretical aspect of a diode, then I recommend you just watch the videos in my channel. Now, and today I've already given you the brief introduction of the diode. And how about BJT? BJT is a bipolar. BJT is so-called bipolar junction transistor. And this device was invented by the same inventor who invents diode. He spelled out the scientist who invents the diode find out this kind of characteristic. It's not much of use. It's not at that time. The usefulness of the diodes is limited because of the lack of understanding. Lack of understanding of the of the vacuum tube. But on the other hand, the Bell Lab scientist has successfully modified this device. Originally, the device has 3 terminals. Sorry, originally, the device here has 2 terminals. The diode has 2 terminals. So what they did is they split this terminal into 2. So what they did is they add another layer. Originally, the device, the symbol of the device is like that, but physically, it has 2. It has a solid in 2 regions. One is the P region, the other is the N region. And and the current go in one direction, then you will witness a current flow after a certain voltage is developed across the junction. And let's say, well, in this case, let's say we put D to represent the so-called diode voltage. And later they use the symbol to represent it. And normally for silicon junction device, the voltage here is about 0.7 voltage. But later on, as I told you, the scientists try to manipulate the device. They split these terminals into two. Originally, we have only one terminal. They end up with a three terminal device by adding another layer here. So first of all, the scientists, three scientists who invent this device, make this layer as thin as possible. So originally, when it's like that, then they make it like this. And they add more concentration here, and they end up with the region so-called N plus. And then afterward, they add another layer, another region, so-called N again. So essentially, they can connect the device in this manner so that the current can flow. And this region also has an interface to the outside world. And this current, there will be current in this region. And now you have a similar device. The device is similar to this one in the sense that you have a P region and the N region. But this time you have one more terminals here. So what they did is they renamed the terminals. We call this one emitter. And they call this one base. And they call this one collector. And now, with this arrangement, they found out the current is very similar. The characteristic is very similar to this one. The only difference is the current through the collector is so-called IC. And they find out so now for a BJT, bipolar junction, bipolar junction device. So it's better to write this correction. Transistor, also so-called BJT. They have a similar characteristic. So you can just copy it. But this time, what they find out is the voltage is not VD anymore. VD is the voltage across this junction. But now the voltage is here. So VBE, because this region is base, so we call this the B. and we call this E, and this one is C. So the voltage across the junction between base and emitter is so-called VBE. And they found out this characteristic. And the current, well, what about the current? The current is not the current through the base anymore, but is the current here. So in other words, they have an entirely different device. The equation is similar, but then the voltage that controls the device is the base emitter voltage, VBE. And the current that actually goes through the device, so-called BJT, bipolar junction transistor, is actually this one, not this one. The current is not IB, it's IC. So they can have current flow, but the voltage that control this current can be separated. So eventually what they did is they analyze it and they find out this characteristic. And you can say that this is just another diode. Yeah, the diode is here. So you have a diode here. And this is B and this is E. Let's see. And, yeah. You have a voltage here, VBE, but the current going through the diode is IB. But I have told you with these devices is not just the diode. So they find out the current can be separated. The current can be separated, measured. And the device has the terminal C. So what they did is they use another model to model the characteristic. And this is the column IC. And ICU is equals to IS VBE VT minus 1. So this is the founding of the transistor. And the model here is called last signal model. Last signal model. And from that time onwards, the scientists used another symbol to represent this device. So you have B, E, and C. So they use this kind of symbol to represent it. This is the characteristic. This is the so-called large signal model. And I'm going to give you about 5 minutes to digest the material so that you know how the semiconductor device is evolved. Initially, we have only a 2-terminal device. At that time, the vacuum tube has already been invented. Vacuum tube is essentially a 3-terminal device. And the scientists use this terminal device and modify it. And they end up with a three-terminal device, which is very similar to the three-terminal device, so-called vacuum tip. And eventually, they found out the characteristics like this one here. IC is equals to this one, and you see that the equation here is very similar to the diode, to the one for the diode. And if you just look into this diagram, you will know that the current IB is essentially the current for the ordinary diode. So you may actually say that what is IB? IB is equal to exactly, because this is actually the original diode. So BEVT minus 1. This is what they have found out. But now by adding this layer, they managed to end up with a significant scale up current. And this current is through the collector terminal, IC. And the scientist has discovered IC is actually equal to this amount. And the amount of the IC is much greater than IB here. So you may say that the actual value of IS here is reduced by the value so-called beta. The actual value is here. So now I presume you have already got the overview of this device. So the next thing that I'm going to talk about is the small signal analysis. To begin with, I'm going to start with this large signal model. So I'm going to free up some space here. For these lectures, I'm not going to focus on the detail of diodes. So first of all, I'm going to copy this device up here. So this is the device. And it's actually the same as the symbol. So we have an E, C, B. So this is the original idea. And now take a look in the characteristic. I told you this is the diode, but now they end up with current similar to the diode, but it has been scaled up. And I'm going to tell you the characteristic. Just now, I have told you the characteristic of the diode. The characteristic of the diode is like this. the diode current, and then the voltage. But I have told you before what the various scientists have found out the characteristic. The characteristic is very similar to the original one. So this is the characteristic. IC equals to IS. And then so this is the finding they have got. Originally, I told you what in a case of diode, you will not have a characteristic like this. And this is 0.7 volts. And at this point here, you have the very small amount of current. And this is so-called reverse saturation current. But for the case of transistor, we have something like this. VBE. And VBE is actually the voltage in here. The voltage across the junction between the base and the emitter. So I'm going to erase this one. For the time being, we don't need this one. So this is the situation. Now, as I told you, this is actually a device with basically a nonlinear characteristic. If you don't know anything about vacuum tip, you may not even know where to start with. And another thing that the scientist has tried is to use this device, substitute vacuum tip with this device. And they apply the AC signal here. So first of all, they bias the device in a way it works. In order for this circuit to work, you have to make sure this junction is in forward bias. It's forward bias in the sense that VB must be bigger than VE. And this junction here has to be reverse bias. Reverse bias in the sense that VC must be bigger than VB. So in other words, in order for this device to work, properly, you have to make sure this voltage is bigger than this voltage, which is bigger than this one. So VC has to be bigger than VB, which is bigger than VE. So now, this is the so-called junction. It's not really useful and in this sense. And the current here is IC. And IC, in this case, is a function of VBE. And if you examine this function, you will notice that this term is substantially larger than 1. So you may just say, IC is approximately given as like this. Now, we take a look here. I have told you, in order for it to work, you have to bias it correctly. You have to make sure VC is bigger than VB, which is bigger than VE. So in order to make it work, you have to get some voltage, make sure it works. So the first thing that we need is to make sure the voltage here is very large. And the voltage at this point is secondary large. Now, that's okay, right? We have this model. As I told you, this diagram is not very useful. It's just for show. Now, how are we going to use the device? Normally, we need to apply the voltage, the disturbance, and this disturbance is so-called small signal. So the first thing you need is to apply the disturbance in the B terminal. And let's say, right, this disturbance is called delta VBE. And this is how it works. You apply a disturbance. So now the actual voltage from here to here is actually VBE, what maybe we call it VBE0. VBE is a combination of two voltage. So now you apply the voltage here, and in this case, VBE is actually a combination of these two voltages. This VBE0 is a large value. It's a fixed value. And this one is used as a signal, which is a very small value. So this one here can be sine let's say yeah, there's a time variance. Say Vm sine omega t. So we use this technique. So now the voltage across the junction is 0.7 volts. But then in order to use it, you may need about 0.6 volt here, 0.65 volts here, and you need about 0.05 volts as a signal voltage for delta VDE. Now, how about the current? The current is difficult to assess. What you can do is you substitute this value back to the equation and you visualize what happened to the current. So when we do that, we have this value, VBE log plus delta VBE. As I told you, this value is approximately given by IS approximately. This value is substantially larger than 1, and that's why we can approximate the value of IC in this way. And now we just use based on the approximation, the expression for the approximated collector current. So we divide the IC. And if you elaborate this, further divide this equation, you end up with a function like this. And if you further, and this one here is actually a collector current when the signal is absent. Yeah, can you see the similarity between these two? So what I do is I will just say this one here is IC naught. And then we can write the equation in this manner. But hang on a minute. When VBE is very small, and when potential function here, you know that when X is small, then this guy here can be approximated 1 plus X. Similarly, we can do the same to approximate this formula. So, in other words, IC itself contains 2 components. IC naught plus IC naught divided by VT. times the value VBE. So if I'm going to explain how it looks like, so basically you have some originally you have VBE here and the value in here may be so-called VBE now. And if you apply a disturbance here, and this disturbance is called small signal. This one here is called small signal. And sorry. Why is this one here? You may have some small signal here. And this one here is delta VPU. And you will end up with a column. The current is IC naught together with the disturbance. And the disturbance here depends on the slope here. The slope is equal to, according to here, IC naught divided by VT. So you have a much more exaggerated current here. And this current depends on the value, depend on the slope. If there's a slope, the steeper the slope, the higher the current that you will get for the disturbance. And the current here is delta VBE times IC naught over VT. So in other words, you can just forget about the right now you have a device here, and you find out the current is a combination, it's a delta IC combination of two currents. One is the large signal collected current, which is a big value, and another one is a small one, small signal, and this one is equal to IC naught divided by VT. So this is what we have end up with for this kind of device, BJT. And we just apply the small signal here, and we end up with a very large, very amplified collected current. Now, you may ask, can we, the large signal is not very much useful here. And you can see that you can use this way to analyze it. It's very cumbersome. The question is it possible just to get rid of the large signal? Should we end up with only the small signal? And we do the analysis more easily. Can we do that? Now we have VBE, right? We have this equation here. And we have the equation here for IC. We have this equation here. Can we just focus on these two terms? The answer is yes. Why? Because if you define this value is a fixed value, a constant. This one is a time variable, IC is a time variable, but this one, IC itself contains two components. One is a constant, another is a time variable. So what we can do is we differentiate it. So what we can do, I'll tell you what. What we can do is we differentiate. We differentiate it and we ignore this value. This fixed value. Differentiate and we ignore this value. And let's see how it goes. I'm going to free up some space here. So now VBE is equal to this one. Can we not just differentiate? If you differentiate this term, then you got let me see. Let me see. You can just look at the differentiated value. Right? Now we visit this equation. Yeah, this term here, IC equal to IS VBE VT. So this is what we have got initially. But now our job is to focus on the derivative of this equation, so that we only analyze this term, and we only analyze this term, and this term is actually delta IC. You can see, yeah, you can still read it. So we can do that. If we eventually, so we end up with delta IC here. This delta IC is basically the same as the same delta IC here. And then, you differentiate it, and we end up with VT. And then, what do we get? VBE. I think, no. This is what we got. But then what is this value? This value is just exactly the same here. So can we not just call this one VBE naught? Because this is the initial value. And this is what we initially have shown. And now, how about this one? Right? If this is the case, can we know? We know that we have this one here, and can we not just use IC naught? That is much easier to manipulate now. IC naught delta VBE. This is much easier. And now from now onwards, we use small letter to represent small signal. We call this one small signal. And this one, anything so that anything that is derivative is so-called small signal. That is much easier now. So why don't we just we can use the disturbance in the base emitter junction to control the disturbance in the C terminal. So instead of using the last signal, we can use another model which focuses only on the derivative of the signal. So in this case, you have a delta, we have a B terminal here, and we have a something like this here. And we have based on this equation, this one is delta VBE. We just focus on the delta. And with this in mind, we end up with a column delta IC. And delta IC, according to this equation, sorry, there should be VT here. Is equals to IC naught over VT times delta V. And now we are almost there. And it's very cumbersome to use the delta operator or every time when we characterize this, the disturbance of the signal, the voltage. So every time when you have a time varying signal, we have to add the delta here. So it's not convenient. So what we can do is we use the small letter to represent it. Instead of using the delta, we use small letter and we use small letter. So in other words, the voltage here will be VBE. And IC here will be equal to VBE. And this is the small letter VBE. And this is the start of the small signal model. And this small signal model is also called pi model. And we can use this model to analyze the behavior, the microsource, the linearized behavior of the small signal. So this is also so-called pi model, right? You can use PI to represent pi model, or equally, you can use pi to represent this pi model. And now I have told you this one is the diol, but you also need to understand that what is this diol? The diol itself, when you zoom in this environment, is essentially a straight line, a linear relations. And the only thing that you can correlate, the only thing that you can make a difference is the slope. The slope is given by IC divided by VT. And but now when you are now looking at the current here, let's say the current IC. Let me see. I need to free up some space here now. In semiconductor, in the BJT, the bipolar junction device, you have a collector current here, you have a base current here, and you have an emitter current here. And what I have not told you is the collector current is actually linearly related with the collector current, the base current. IC is actually equal to beta times IB, where beta is the so-called forward current gain. Forward current gain. So in this case, you may know that the IC, if you differentiate this term, if you differentiate both sides of the equation, you end up with delta IC equals to beta delta IB. So in other words, right, IC is equal to beta IB. You have already known that you have this value here. And for the time being, let's, the question is, what is IB? Okay? IB is the small signal current here. Based on this equation, IB is, if beta is moved to the other side, you will equal to beta. And I have told you what IC is equal to this amount. So in other words, it's equal to IC, not beta, EBE. Now for the time being, let's say we call this term IC naught divided by VT. We call this term GM. GM is so-called the transconductance. GM, transconductance. So in other words, right, we have beta GM divided by beta VBV. So this is IB. So you have a voltage here and then the value here. So you can rewrite this equation. You can say VBE is equals to beta times GM. And then IB. And there is a special term for this value. This is so-called the R pi. So from here, we have voltage VBE, and we can just, based on this model, we can actually linearize the device, the base emitting junction as a resistor. And this resistor is R pi. And the value of R pi is given by this amount. And this one is VGM. So this is the so-called pi model. Pi model. I hope you can digest the material. I am sorry that the material is not well organized, but at least you'll get some memory background. So this is the pi model we get. And this pi model is exactly the same as the pi model that we can look for, that we can see in the textbook. And if you have any question, please leave your questions in the comments box underneath the video, and I will try to answer you separately. Thank you very much.